You should be familiar with a conditional statement and how they're structured and written symbolically. Now, we will use this as our starting point to answer the question, what is a biconditional statement, and how do you determine its truth value? Next, we'll learn how to construct compound statements and determine their validity using Venn diagrams and truth tables. A conjunction is a compound statement that uses the word and to join the two statements. To make the two statements about Emily into a conjunction, we can join the two statements into Emily likes to eat sandwiches and Emily likes to eat soup. Or we could just say Emily likes to eat sandwiches and soup. The symbol for conjunction looks like an upside down V. So that if we were going to go ahead and represent the entire compound statement, we can say P and Q. A disjunction is a compound statement that uses the word or to join the two statements. Now, to make the two statements into a disjunction, we can join the statements into Leo washes the dishes or Jacob washes the dishes. Now, the symbol for disjunction is going to look just like a V, and we can represent the entire compound statement as P or Q.
Here's the thing about compound statements. Sometimes they're hard to evaluate.
But good news, Venn diagrams can help.
How? Let's take a closer look.
For these examples, let's say P and Q are two statements. Where do these statements go in a Venn diagram? Well, it depends on what kind of compound statement we have.
With a conjunction statement, let's represent P being true inside the blue circle and Q being true inside the orange circle.
As you might know, conjunction statements use the word and. So we're looking for where both P and Q are true. Do you see it?
If you're eyeing that spot where the circles intersect, you got it. That's where both P and Q are true.
But what about disjunction statements, the ones that use or instead of and?
If either P or Q is true, the statement is represented by the entire diagram. Every part of it falls under that statement.
Now, you might be thinking, hold on, don't or statements mean it's either P or Q, but not both? I mean, that's how we usually think about either or statements, right?
Well, with logic, it could be one or the other, or both. So if I said Leo or Jacob washes the dishes, that could mean either Leo or Jacob does the dishes by themselves.
But it could also mean they both wash the dishes, together or at different times.
That's just one of the reasons Venn diagrams can be useful.
Seeing conjunction and disjunction statements on diagrams can help us evaluate these compound statements.
In logic, we study statements that have a truth value, either true or false. Frequently, we make arguments in logic, and in logic, the arguments are justifications for why a statement is true. Logical arguments use simple and compound statements both, including conjunctions, disjunctions, and conditionals. In order to check an argument, you must know whether an individual part is true. This is where truth tables come in. They're helpful for compound statements because they organize the possible truth values for the pieces of a compound statement. This, in turn, helps us to evaluate the truth value of the compound statement. Let's check out this table that we see, and we see that P and Q represent two statements. So the first two columns will contain the truth values for both P and Q, and we must be sure to get every possibility of them. So down the column for P, we'll start with two trues, followed by two falses. While down the column for Q, we'll alternate starting with true, then to false, then to true, and then to false. And in this way, what we've done is we've gone ahead and looked at every possibility of true and false for the two statements P and Q. The very last column that you see right here is going to be the column for the compound statement P and Q. So let's take a look at P and Q as our column header and revert back to each of the components. So first of all, what do we know? We know P and Q is true if both statements are true, and false if either P or Q is false. So the next three rows would all be false. Well, how does this apply to mathematics? Let's take a look at a compound statement, and here we have one shown. It says prime numbers are odd and greater than 1. So we could say prime numbers are odd and prime numbers are greater than 1. And when we do, we then form two statements. Prime numbers are odd, which we'll call P. Prime numbers are greater than 1, which we'll call Q. Now, not all prime numbers are odd. For example, 2 is not an odd number, yet it is prime. So what this tells us is that the statement P is false. But all of the prime numbers are greater than 1. So this tells us Q is true. So based on what we know with everyday language, we know the whole statement cannot be true. This whole statement being prime numbers are odd and greater than 1. So what we would say is that P and Q is false. Now, if you would, let's see if we can see this reflected in our table, and I believe we can. We can go ahead and see that in the very third row, P is false, Q is true, so P and Q is false. Now it's your turn to see if you can understand the truth table for a disjunction. We have used truth tables for conjunction and disjunction statements, but now we're going to use truth tables for the lesson question, what is a biconditional statement and how do you determine its truth value? So we'll learn what a biconditional statement is and we'll build a truth table for it. Biconditional statement is a statement that can combine two statements by using the word if and only if. So the symbol for this biconditional statement is a two-sided arrow. You can guess that the biconditional is related to the conditional because of the word conditional, the word if, and also the symbol, which kind of looks vaguely like the conditional. Now, if we were to write the conditional statements P then Q, it would be the compound statement, if Jessica is sleeping, then she is in bed. The converse to the conditional statement is constructed by switching the hypothesis with the conclusion. So here the converse would read, if Jessica is in bed, then she is sleeping. So we finally get to the biconditional statement, which says Jessica sleeps if and only if she is in bed, which we could write as P if and only if Q, or even Q if and only if P. Now, a biconditional statement states a conditional and its converse statement. So that's what we'll do. We'll take these two statements here, and we'll join them with an and. So we'll have P, if P, then Q, and if Q, then P. Biconditional statement is a statement that can combine Let's build a truth table to see when a biconditional is true. We can use an example to help us. We'll let P represents Henry babysits Caleb, and we'll let Q represent Caleb parents are working. The conditional if P then Q is if Henry babysits Caleb, then Caleb's parents are working. And so that's what we see in this very first column that we have to fill in. Now, if P and Q are true, then the conditional statement is also true. If P is true and Q is false, as we see in the second row, then the conditional statement is false. Why should this be? Well, if Henry is babysitting Caleb, but then Caleb's parents are not working, there's got to be something wrong with the argument. So the conditional is false because the conclusion should be true when the hypothesis is true. Go to the third row and we see when P is false and Q is true. Now, this is just a little bit difficult to grasp at first because we commonly think that P causes Q. But in logic, it's not necessarily the case. In logic, the conditional statement is true because the conclusion is true. It's like saying if Henry is not babysitting Caleb, Caleb's parents could still be working. Maybe Caleb has a different babysitter. But what matters is that the conclusion itself is true. And so therefore the conditional is true. Well, let's go ahead and take a look at the last row where both P is false and Q is false. And logic will assign a conditional value of a true statement. And this is because it does not refute or contradict the if P then Q. In other words, if Henry does not babysit Caleb, then Caleb's parents are not working doesn't really refute that when Henry actually does babysit Caleb, then Caleb's parents are working. Let's fill out the truth table for the converse. If Q, then P. So now we have if true, then true. That would be true. If false, then true, as long as the conclusion is true. We're going to have a true conditional statement. True followed by false would be false, and two falses, well, that would be true. All right, now it's time to turn our attention to the biconditional. So when we take a look at the biconditional, we have to remember that a biconditional is nothing more than a conjunction between if P, then Q, and if Q, then P. So as we go to fill this out, we'll go ahead and say to ourselves, as I look across the first row, if I have two trues here and here, I'm joining them with a conjunction, then the statement is true. That occurs in the first and the fourth row. But with a conjunction, if either statement is false, which occurs here, then the conjunction is false. Now notice, if you will, one byproduct, which is that if we look at the very first two columns for P and Q, we can determine if the biconditional is true or false. Because notice what we're seeing is that if P and Q match in truth values, they're either both true or both false, then our biconditional is true. While if they don't match in truth values, then our biconditional statement is false. Determine the truth value of the given statement. A quadrilateral is a square. If and only if it has four right angles. Now, let's determine the truth value for the two conditional statements. First, P implies Q. This is going to be true. If a quadrilateral is a square, then it does have four right angles. But for Q implies P, the converse, if a quadrilateral has four right angles, then it is a square. This isn't true. This is false. And it's false because we can go ahead and sketch a rectangle. This is a quadrilateral. It has four right angles, but it isn't a square. So this biconditional statement that we're seeing is false. Well, what do we have to add to the biconditional statement in order for this converse statement to be true? We must know that all four sides are congruent in order to guarantee the quadrilateral will be a square. So I'm going to add that in. I'm going to add in and all four sides are congruent. A definition is only good if both the conditional statement and its converse are true.